discussions for second TV, because we'd like to manage our whole syllabus within what time we have. But then the discussions are not for sequence. So the ongoing discussion will resume when we meet physically tomorrow. And B. And for section C, we already covered lecture on noise. This is the first thing we'll discuss today. The verification. But our discussion. So therefore, we'll discuss the event today. By the way, am I properly audible? Can someone on hear me or not?
স্যার কথা শোনা যাচ্ছে কিন্তু মাঝে মাঝে একটু অল্প বোঝা যাচ্ছে।
Really? Okay, maybe I have some mobile data. Maybe let me switch to the Wi-Fi. So that sound better now?
Yes, sir.
Okay. Please know when I'm switching in. We have three options here. Okay.
আবার কেটে কেটে যাচ্ছে।
Okay. Okay, let's see how it goes for a while. And so here's the short discussion. The awareness receiver. Self
স্যার কথাগুলো স্পষ্ট না স্যার, কেটে কেটে যাচ্ছে স্যার।
Again, switching back to mobile data. Is it error or error? How's it now? Is it different or error? The audibility is better. Is it not? Or you can't hear me any?
স্যার দুইটাতেই কেটে কেটে যাচ্ছে মনে হচ্ছে।
Last option. How's it now? How's it now? The same quality?
বেটার মনে হয়।
Better. Okay. But what is the actual black grade? That's why I give multiple options. Okay, so let me know if you have any problems again. Okay, so let me start recording. Okay, no. This is the little different. Okay, we're going to discuss noise. And every material has some noise inherently, and the wireless receiver to regenerate a signal, like undesired noise, it has to also include, and there are multiple sources of this noise. It's something I'm going to discuss today, and it may come from the external environment through the antenna, or it can be generated internally by the circuitry. And depending on the signal quality, your their signal and the noise, you will experience some problem. Uh, Internal noise generation, that a few sources. The first one is the most important one, thermal noise. It is material because of the different vibration. Helps the signal generated. If you hold the top of the sensitive oscilloscope across a decibel element erased, you see some fluctuations on the display. So, uh, it, some signal is always generated. Across just a decibel, no other source, erased or inductor or whatever. Meaning that every method has some level of vibrations. Yeah, these vibrations depend on the temperature and directly related to the indicator. Like, can some vibrations can drop, could drop to zero temperature, to temperature. And certain terms of microscope. Either noise sources are less important for us. Shortness of frequent noise exists in the case of active devices. Shortness is due to random factors of failure, little noise to the raise the frequency. As the noise is caused by ionized gas, and noise. Mountain noise is even less important thing. Uh, look total of this nature of the experience. Noise low. So, the out of the general noise consideration, we may focus on thermal noise, and we may include only thermal noise in our equation. Of course, noise can also come from external sources, like from the sky or stars, like lightning. Some of them not shown here in the list are actually uh, called interference, but this particular discussion will consider them as to human signal with noise or interference is the ignorant. And sometimes it in itself is not generate or it's the other take of generate other then you may call it noise, but it actually interchange the term interference is more common when it is delivered to create a communication. It's used is anyway, so microprovince or the determined device of the generation. Noise floor is it's an indication of the minimum noise level that you have in the communication source. Like in your particular circuit, the general noise level, it may be less. something fitting instantly. That is considered as noise floor. Inner noise floor. Yeah. So, okay.
Yes, sir.
Maybe once again I can switch to no experience today. I switch to mobile data. Mm, yes, well today. Is it little better or little better? So noise level is the noise uh, level is you have from the noise of different sources. The related noise.
Sir, am I audible, sir?
Yes, you are.
Sir, maybe your microphone, the problem is in your microphone. If you change the microphone.
Uh, yeah. It's only one.
Sir, it's not actually clear, sir. There's some noise background. Sir.
Uh, I think I whether I avoid my headset and use the microphone of my laptop. Okay, let's see how it. Okay. Now could you tell me whether it's better or not? Okay, is it better than before? Or worse?
No, it's better than before, sir. It's better now.
Better now. Okay. So
Yes, sir.
just direct microphone of my laptop. Okay. So, it's okay. Okay, now noise floor means some accumulation of noises from different sources in a general noise level in your system. Like it's that you may have fluctuations like this uh, as you test it on some oscilloscope or something. So that's on score for your receiver circuit. Actually, it can be for any type of circuit. Now we would consider only the thermal noise when you calculate this the noise because other noises are relatively lower and they may be neglected. The thermal noise you can calculate using Boltzmann constant in the temperature. And let me let us assume that for a particular case of element, this is the noise, um, thermal noise you get when you measure across the device. And the current temperature in cell in absolute temperature is K-degree Kelvin. Now, the there is a formula for Planck's body radiation law, which gives you that noise voltage. So this expression uses Planck's constant, Boltzmann constant, and from this voltage expression, we can calculate the power. But before we do that, we're doing some approximation using Taylor series expansion, and that results in a simpler expression for voltage. Very simple. It's for Rayleigh-Jeans approximation. Then we calculate the power from the particular passive element. So to calculate the power, we actually connect another resistor load of similar value using Thevenin's equivalent circuit. But we take the noise power over particular frequency range. So you have noise generation different frequency at many different frequencies. So if you measure over a wider frequency range, noise power would be higher. So it depends on the frequency range of which you're measuring noise power generated. So we limit over a particular frequency range, B, we let the signal pass through filter, bandpass filter with B bandwidth, and then we calculate the power. So the power is Bn per by 2R for P, and we have this simplified expression. So using that, this is the power we get. This is the normal noise power okay, from an element where T is called the thermal noise or equivalent noise temperature. So this tells you how much T itself gives you how much noise it is generating. Equivalently, you can express the noise in any source using this equivalent noise temperature. So just we need to remember this formula KTB. Poisson constant multiplied by bandwidth. And like for this example, the equivalent noise temperature is 75 degree Kelvin, and the bandwidth is 27 megahertz. So we're calculating the noise power. So if you take the absolute values for all KTB, then you could just multiply them. If you want to calculate in dB, because the power you may, if you want in dB, then you can also use the dB values for all of them. Like just for K, T, or B, you take 10 base logarithm and then multiply by 10. And whatever values you have, just add and then results in the noise power in dB. Just try to get this point how you switch back and forth between normal values and dB values. Noise figure is for a stage of your circuit. The circuit itself adds some noise. Every element adds some noise. So every stage in the circuit also adds some noise. So the input SNR is better than the output SNR. So the stage itself adds some noise. And this ratio, the ratio of input SNR and output SNR, is called noise figure for that particular state. And it is always higher than 1 because it has good words about it. And for a particular state, you can show this way. Analyze at that SNR condition, the input and output level. Now, first, wireless link where noise is dominating, the unwanted power can be considered the noise. In the case of PN calculation, you just input the noise. But if interference dominates, then it can be much higher than noise. And then PN condition must consider the frequency, the interference, and noise may be ignored if it is too low. So note that for LOS links, the interference can be very negligible because you have separate phase for the signal transmission and confined space. So there's very little chance that some signal from outside sources will affect. So in this case, the PIN, assuming that the carrier or the desired power is the same, the receiving end, unwanted power limits your CINR and that limits your data rate. Now, the unwanted part is mostly the noise because your interference is negligible. The inner links can be called noise limited. Noise limits does not, if you can, I mean, improve your noise quality, make the noise level lower, then that can actually improve your CINR and the data. So the links can be considered to be noise limited, whereas non-LOS links can be considered to be interference limited because frequency reuse may cause high interference to you itself, but generating the same thing. And then these the LOS links are usually interference limited because their interference is more computationalized. The CNN is mostly dictated by the interference. So interference, these are for interference limitedly, noise limitedly, because just because noise interference are dominating. So right here on the left side is the last slide here. On the left side is the noise limited system. You see that as you move your receiver from TX, as you move RX further, then definitely the carrier power, the reset power drops because of the increased loss. And the noise level is constant at any distance as marked in blue in the profile. The ratio between P and N gives you the CINR value. And that you may have some minimum value you have to maintain to satisfy your requirements. So at certain distance, the ST drops and CINR also drops to that minimum tolerable limit. That gives you the maximum distance, possible distance for a receiver, or that's the coverage on the transmitter. Beyond that, you cannot operate the spectrum. Whereas in the case of interference limited, where you say that you yourself is generating, using the same frequency somewhere else. So red TX is the source of interference, same signal frequency. So as you move your RX further from TX, you get closer to the interference source. So the interference increases. So on the one hand, C drops, and on the other hand, I increases as you change your location. Now here, you still have N at that level, but that is much lower compared to your I. So it's interference limited. Interference dictates more fundamentally how you where you actually stop, what can be the maximum distance. So at certain distance, your CINR is reaches the minimum tolerable limit, mostly because of I, with little contribution from N. So now you see that it can be called interference limited. Any questions so far? If not, we'll move to topic link budget. Thank you. Now, let me jump to the last slide. We will do some calculations. We have a proper estimation of our requirement. We already know that the PR, the receipt power, can be calculated from PT, PTR, net loss, and all that. But there are some small components too. And using them, we can have a more precise calculation of what receiving power we may have, and also what we may actually need, considering the noise conditions or independent conditions. So based on that, we can then more precisely calculate our transmit power requirements. So this kind of calculation, incorporating some small effects, called link budget. You have a total budget calculation for all the way. So like say for this stuff like link, uh, some atmospheric absorptions are considered in, in so and you discuss what other things you have, but some small effects are also considered. That's how you calculate how much your I mean what your current condition is. Based on that, you can also decide the cost of recovery. So we will do this link budget calculation for two example cases: satellite as an example of LOS connection, and a cellular link as an example of non-LOS. So there will be two examples to cover through this discussion. So now gradually we'll get there. Well, yeah. So the purpose of the link budget is to determine the transmitting end requirement, how much power you need to transmit, or what may be your EIRP. Or secondly, between uplink and or to determine how far you have the coverage, where the receiver can be placed at the furthest.
Sir,
Yeah.
are you sharing your screen?
Oh, yeah. Oh, sorry, I didn't. Oh, I forgot it. Sharing. I mean, I thought I was sharing. Sorry. The figures I was showing, I mean, I thought I was showing, like, I mean, this slides where I show the calculation. This is for calculations of satellite link, and these are the calculations for cellular link. So, but we'll get there at the end of our discussion today. Now we are here. This is the slide I was discussing. The purposes of the link budget to determine the transmit power as EIRP, or to determine how far you can cover the maximum distance. And secondly, the uplink and downlink have some differences, and you need to ensure that you fulfill the requirements on both sides, and so then you can ensure the balance. The uplink can be more challenging, and you may actually have to accept something on the downlink to ensure that uplink is properly working, as you see shortly. But how you go with the whole design? Well, you first set some maximum target maximum BER. Okay, that I need to ensure this much BER for my application. Like you remember that we shared a table with different QoS requirements. Say for voice, we had BER in terms of PLR. The minimum error they make like 1%, 10 to the minus 2. First, for non-real-time applications, our minimum error requirements was 10 to the power minus 6. Okay. So these are like your BER, somehow indicative of BER. So we first set some target maximum BER. That depends on your type of application. Also, it depends on the type of coding. Like your coding speed can be better to be able to correct the BER. If you have a stronger, like a very strong LDPC coding, then a poorer BER can be manageable. So it depends on your type of application, the strength of your coding. I'm talking about line coding, I mean turbo coding or LDPC, this kind of coding strength. So based on that, you set what minimum maximum BER you can work with. Then based on that, you select your minimum CINR, because you know that CINR is related to your BER. So what then from BER you calculate the minimum CINR that we can tolerate. But this CINR can also depend on modulation and receiver sensitivity, like your minimum tolerable CINR. Well, say your modulation, if you have some higher modulation, then your minimum CINR will be null, right? Because for the same CINR, this high modulation causes some issue. So what modulation level you may be working with actually dictates what minimum CINR you may set. It also depends on receiver sensitivity. Okay, let me go back to one slide that I missed earlier while discussing the link adaptation. Just hold on. Slide number 28 on link adaptation. I probably mistakenly skipped. Now I'm going there. Probably I explained it one of the three sections. Receiver sensitivity tells you what minimum CINR your receiver can work with. Of course, for some satisfactory service, and the satisfactory service may be some specified BER. So you have some BER requirements that this is specified BER I1. I cannot tolerate a lower, a higher BER, a worse BER. So for this specified BER, this is the minimum CINR that the receiver can work with, or the receiver can provide this BER with this minimum CINR. It depends on the quality of the receiver. Like the expensive phone can work with worse radio conditions. The same BER, it can produce with a worse or a lower CINR, because the more expensive phones has some additional features like interference cancellation techniques. Few things are more carefully designed. So all receivers are not of equal quality, or they don't have. I mean, it's the same CINR can lead to different BER for. I mean, cheaper phones. You have higher bit error, like the phones that uh, features of ITUs are usually cheaper. So for the same radio link condition, the bit rates are higher. But the IT students usually use very expensive phones. So for them, the errors will be lower, the same radio link quality. So you may have some specific BER requirement, but for that, your phone, it depends on your receiver quality, what CINR can be minimum allowed. And that is called receiver sensitivity. What minimum receive power level you can work with. Okay. This is usually given in terms of receive power level, for which you get the minimum allowable CNR, so that you have the full some specific requirement. But receiver sensitivity also depends on the noise floor, the say the let's say there's some input cancellation techniques, or I mean different things how the signal is modulated on the carrier. Anyway, so now we go back to our link budget. We say that the minimum CINR that you use as your target depends on the receiver sensitivity, actually the receiver quality. Uh, so based on this CINR, you set some target minimum receive power level. But I mean, you have to take your noise or interference from which you calculate minimum power from your target minimum CINR. Once you have this minimum receive power value, okay, PR for PR you get minimum requirement. Then use the link budget that we're going to discuss to set the transmit power level, considering all other effects in between. Okay? So you can calculate the transmit power level. And in or it may be the other way around. You have some particular transmit power already set or pre-designed, and then you can set calculate using link budget the maximum distance for your receiver. Another point, I mean, I mean, we will have to include it in our calculation. Like this small things we are including now. It's called fade margin. Well, the signal is fluctuating itself in reality, especially for non-LSM or fluctuates too much. So when you say that, well, I would ensure this much power, actually the power level is fluctuating. So you need to actually allow some margin when you say that I need this much power because of this fluctuation, so that when it drops, you still, I mean, you're still somewhere close to your minimum requirement. So allow some margin. Like the red mark is the minimum your requirement receiver threshold, and the fluctuating signal has this yellow level as the RMS value. The difference between them can be taken as fade margin, but in reality, fade margin also depends on some choice of the designer, the engineer, how he wants to take. But anyway, so fade margin allows you to design to ensure your power level even when it drops to some low level because of the fluctuation. Now we are explaining link budget using an example. Like it's for an LS link for a satellite, and the output power is 20 watt. Okay. The for satellite is called transponder, which receives from one end and then transmits the direction. It's called a transponder. Anyway, so it's like your transmit power. That's 3 watt, and the antenna gain is given. So PT, GT are given. The bandwidth is given, which you're transmitting. The frequency band given, and from a real life calculation. So some values may be unnecessary for us. Like the frequency band we won't need actually in the calculation. But you see the antenna again on axis. I mean, see the line on the third line from the bottom. That is the uh, that's the okay, that's GT. This is GT. And the frequency, the operating frequency is 4 gigahertz. At the bottom you have your for LOS link noise is it's noise limited. So we won't have any interference. So unwanted power will be calculated using KTB. Now for downlink the link budget calculation like this. Say for PT, now we do the calculation. This is some information given in the question in the exam. You may be given some information based on which you may have to do this kind of calculation. Like for when you are calculating in DB, that's how you can calculate. And the second point is, as I said, the link budget includes some small effects. Well, the transponder output backup something that okay, you It's like amplifier itself first. It, give me a second. I'll come back to this point, but for now, we just have to. It's always a negative value, and that you have to add. I'll at the end of the class today I'll explain what it is. Have a separate slide. And it's about the amplifier. And the satellite antenna gain GT is given. Another station here, the antenna is given. When the satellite is for downlink, so the satellite is transmitting, the antenna station is receiving. So this antenna gain is the G. And now different things on the way, like the free space path loss. Well, that depends on the distance. So for satellite, this is the free space link calculation. Free space calculation link will always be used. That is for direct transmission between 2 points. Okay, so you use the path loss using the expression of that equation. Then if for the distance is for a geosynchronous satellite. I'll give you the distance for that. Uh, it's our space. Little more than 22,000 miles. So the altitude of the satellite is fixed. So it just depends on your lambda what endpoints would be. The age of beam loss for the satellite. Well, this indicates that the satellite radiates over a particular region on the Earth, on the face of the Earth. But you see, on the both sides, you have the particular gain that we are using for GT, right? But gradually, the signal a little bit decreases as you move from the both side on the receiving surface. Right? On the both side, you have the maximum receive power. But gradually, the receive power decreases as you move from that point. So you still have covered over a wide area, but the receive power is not the same everywhere on the covered area from the antenna on the face of the Earth. The both side is the maximum gradually. So you have some typical loss. This is called age of beam loss. Like when you consider a particular covered area, then the age of this area has the minimum receive power. And the difference between the both power on the both side and on the age is called age of beam loss. So that is like minus 3 dB and 3 dB. And then clear air atmospheric losses. So this data could be available with the question. And some other small losses are also included. And then you calculate the receive power station. From PT, you calculate, with PT you add GT, GR will also be added, but other things you have to, these are some losses that you have to subtract. So in the link budget, you use positive negative signs. And finally, you calculate the receive power. But you have actually certain PINR requirements. As we earlier showed, some PINR requirements for your this for in link budget. And the PR we already actually estimated minimum. We have this estimation, but depending on noise or you have to calculate PINR. So now we calculate the noise. The noise temperature is given 75 K, and both one constant, and the bandwidth is given 27 megahertz. So with that, you calculate KTB in dB, and you add them, and then you get the noise. So this was your receive power, like C, and this was your noise. So you subtract N from C, and that's how you get CIN. So this is the CIN. So now you take whether this designer fulfills your requirements or not. If not, you can change your PT or some other things so that designer fulfills your requirements. Just like it get PT. This is another example. I think you can go through it yourself. Have any difficulties? We can discuss it in the class. This is a book from this from the book of Brad. Right? Brad was Brad took my class on satellite communication at Virginia Tech. In his book, that satellite communication was the most popular book in the world. Okay, again, please take it yourself. Okay, we let me discuss the example of cellular link. Then we wrap up. For cellular link, tap loss, I mean, tap balance can be an issue because downlink and uplink has a difference. In the uplink, your phone may have a lower maximum power transmission limit. Like in this example, we have no issues. The maximum power transmit capability, I mean, on the left side you have the base station, on the right side you have the phone. So in the case of downlink, the blue line is showing the change of power over the distance. So based on transmitting at certain level, gradually the power is dropping at the distance, and when in the phone end, the power drops to a limit, which may be satisfactory. The pink one shows the uplink condition, the maximum mobile power transmission. Gradually the power drops, and the minimum, when it gets to the base station, it still fulfills the minimum requisite power requirement. So now we have no issues. The, the minimum requirement is fulfilled at both ends. And we have the same path. But you may have an issue when you increase your distance, but the phone cannot further increase its power. Already reached its maximum power limit. On the base station side, you could further increase. This is more capable. So as the distance has been increased, from the previous slide, we have increased our distance in this slide, putting the mobile further. So on the base station, you increase your power level. And so you still fulfill the minimum power requirement at the phone end. However, in the uplink, you cannot increase your power further because you have already reached the maximum power level. So at the base station, the minimum, the power drops below your minimum requirement. So you have an actually path balance issue. The path is not balanced. You don't fulfill the requirement in one of the two lanes. It's an unbalanced. So the resistance cannot hear. Okay, so you need to actually find out the maximum distance considering the uplink, or which is less power capable. So this something will do is an example. Again, the noise power you have to calculate for display KTB. And for antenna gain, well, base station gain is usually 6 dB to 16 dB. For mobile, we, as I said earlier, it can be 0 dB. Another thing is cable loss at the base station. Well, when you transmit power, you put your amplifier at the top of the power. Well, and so it's actually optional. The power amplifier before transmission can be the actual circuitry is at the bottom, and your power amplifier can also be located at the bottom of the tower. Then you connect this amplifier to the antenna. Antenna must be located at the top of the tower, and this connection cable can actually add some loss. So the power you're calculating, okay, that this is the power my amplifier is providing, will have will uh, have some lower value when it gets to the base station, to the antenna. So the cable loss is called cable loss that you have to subtract whatever from your or your amplifier is generating. Okay? So normally the cable loss is given, I mean, in terms of such dB per 100 feet or something. To check how long your cable is standing. Okay, so the bottom line is cable loss you have to subtract. So now in the link budget, you put different things with proper sign, positive or negative, whether you have to add or subtract. For this example, we just have to, for demonstration purpose, we are using a channel bandwidth 30 kilohertz, which is not used with the system. Anyway, the temperature is 70, which is used for your noise calculation. So thermal noise we calculate using KTB in this bandwidth, this temperature, and Boltzmann constant calculate thermal noise. Noise floor is the is calculated uh, and that's your noise floor. Once you calculate from KTB, you calculate and noise figure is given. So when the cable loss per 100 feet is given, from which you calculate the cable loss or cable loss, and that is D. So this D you actually have to okay, see if we follow the expression at the top uh, top left corner, C by N you calculate subtracting N from C, and this C in this table is marked as M plus K plus L minus D minus H minus A minus G. How are they? And N is A plus B. N we already explained, the total noise flow is A plus B. Now on the left side, the AM is the input power. Uh, 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 Okay, so AM is the power that you have at the receiving end. At the receiving end, whatever power you have in the air is M. And then you add your receiver antenna gain to M, so M plus K. L is the diversity gain. Like we explained some diversity before mid-semester in the GSM RNP discussion. There's some diversity discussion. So diversity can increase, antenna diversity can increase the effective power. So that you also add. So the power level in the air is AM, then you add your techniques like the antenna gain, K, then because of diversity, you get to fill the real power a little more, and that L. But then you subtract all the other loss like effects, like the cable loss that you have to subtract. So D. And the H you see them, I mean, look at the table and see the rows, H. H is the body loss. Body loss means when you are getting the signal, say in the downlink, uh, because of your body, some power may penetrate through your human body, and that you can incur some loss. Or you may be inside a vehicle, so the vehicle body can add some loss. In the downlink, this kind of losses you may have. So these things you have to subtract. Like so DE, see the expression on the top corner. DH, these things are subtracted. I is vehicle loss. These things you subtract. J is the loss if you're inside the building. Then the BPL is subtract as J. Okay, so DH, ID, these things is subtract. So that gives you the carrier power C. C minus N gives you F, which is your CINR. But we actually want to calculate M from this part of our discussion. So from M, we rearrange the whole thing. Now all the letters we rearrange. Okay, now the link budget, in this link budget, you calculate for both uplink and downlink, but the calculation is a little different. For downlink, you have this body loss, vehicle loss, whatever we have just explained. This thing you explain because the mobile is the receiver. From the base station, as you're receiving, you may be inside a vehicle, you may be inside a building, so you add this loss. But in the uplink, you transmit, and I mean the base is not within some building or within some vehicle. So those fields are vacant in the uplink. You see there are two columns, uplink and downlink. You don't have those, no values against those labels. So there are a few things that you have values in the uplink, and there's a few things you have for downlink. Like in the uplink, you could have that diversity applied because in the uplink you can put multiple antennas on the base station, and you can use this diversity gain. So for diversity gain, K, you have some value in the uplink, but not in the downlink, because on the mobile phone you cannot put multiple antennas. So there's this value 0 there. Now, similarly, say for cable loss, in the case of uplink, in the case of uplink, base station is receiving at the antenna, then at the receiver, after the antenna, after the cable, you get some power. But in the downlink, your mobile does not have this kind of cable loss, so that field is 0. So this is how you calculate both in the uplink and downlink what minimum value you require at the receiver end in the air. So M is for either uplink or downlink, the minimum required power in the air in front of the receiver to fulfill the minimum PINR of the receiver. For receiver to maintain certain, like you see the column C by N in the parentheses in the table. I'm marking the column which has F on the rightmost column. Mark F. So there you see that the minimum BI requirement is 33%. For that, the CINR is set to 15. Set to 15. That is your F here in the expression. 15 GB. So to fulfill this minimum CINR requirement, or to fulfill this 3% BI requirement, this is the minimum power you need. One more slide, please. Give me 5 more minutes. So we started 10 minutes late. Okay. So now this is the second stage of your calculation. From the previous calculation, this minus 125 dB, 1.15 dB for uplink, minus 97.1 dB for downlink is the power calculated. So now we put them here. You see that there is a row, effective minimum input. There you put those values marked in red, yellow, okay, for uplink and for downlink. So this is the power you have. You require the display end minimum. And then do the calculation for uplink first, because that limits your, I mean, as you showed earlier, that because of your uplink power, transmit power may be limited. So to maintain that balance, do the calculation on the uplink side first. So there, you have those values given, like what the maximum transmit power on the uplink is. So it is given 16 watt. We calculate in dB, 27.8 dBm. Then the transmit power, I mean, the gain of the mobile is considered zero. So your GT is zero, and so EIRP just still 27.8. And then body loss or vehicle loss, okay, these losses are added to your transmitting, but this power is, I mean, this transmit power uh, has to go through the body or your car body. So you subtract these losses, and there may be building, you may be inside building. In this case, you are not inside building, so for BPL you have zero value. But then you also add some paid margin. Okay, so uh, sorry, you subtract some. I mean, this thing you must subtract. Okay. So from this this E is the transmit from ERP, you calculate this way equals to A minus B minus C minus D. And this J transmit power that you need to calculate is E minus F minus D minus H minus A, because these are the losses. With considering paid margin, you also assume that your actual power is lower because of the fluctuation. Your actual power is little lower because it drops to some lower value. So that's your case. So then this is the effective transmit power you have in the uplink at the mobile end, and minus 125.5 we calculated in the previous slide at the